Hey everyone, today we'll be going over binary search trees today. Particularly we will be focusing on an introduction for such and then building out our binary search tree header file to print out our necessary trees. And without any further hesitation, let's get started. And now going over binary search trees. So binary search trees overall are a type of data structure that are very similar to graphs and trees like we have discussed, except for the differences is that they typically would have two directions since binary. And specifically, like trees, binary search trees can only have two children per node. Their time complexity is O log of n, along with their space complexity being O of n. Keeping it very efficient when it comes to time and space complexity overall. And there are a wide variety of different trees that we'll be able to go over, namely, but trees are typically built, as we have already mentioned, as nodes, but in binary search tree, we have to abide by this rule. They can only have two children per node overall, so it cannot fully expand to a regular tree. It will fall under binary search trees as well. And in our example that we have over here, we have a given node, and then we also have a class that we have, a public instance, with a private instance over here for necessary functions that we would have in order to either insert a following node, perform in-order traversal, search a specific node as well, and be able to output the necessary formats that we need for a binary search tree. We'll be going over more in our practice examples that we need to go through, but overall, this is just the principal binary search tree. It's just a tree, but it can only have two children per node. It's very self-explanatory, but it's also very expensive to be able to build out. So now let's go over and focus on our practice problem. And now going over a binary search tree. So overall, what we need to do is that we need to implement a binary search tree in the different following formats. We have to implement a full binary search tree, complete, perfect, degenerate, balanced, and then finally unbalanced, and we need to perform the following operations. We first need to insert a node into the tree, remove a node from the tree, perform an in-order traversal, perform a pre-order traversal, post-order traversal, and finally we're going to perform breadth first search and depth first search, both iteratively and recursively, in the context of a binary search tree. So, and in this video I have the following images at the same time over what we will be building out, namely, and now let's head over and let's focus on our full tree. And now we're going to be focusing on building out our full binary search tree, but prior to, I'm actually going to be creating a header file that we will be using throughout all of our different binary search trees as well. So to be able to kick things off, I'm going to create a new file, header file. I'm going to call this BST and create this right here. There we go. So this will allow us to be able to print out the various trees like we did before in our graph simulation at the same time, except for we're focusing on binary search trees, so we know exactly what we're printing out simultaneously and be able to go through it step by step. And this will be great practice for us to be able to get further accustomed with the C++ syntax, so feel free to code along as well. So first thing I'm going to do, I'm going to include the libraries. We're going to have include iOS stream, then include vector, include string, include CMath, include unordered map, and then we'll be using namespace std. We're going to structure a public node to use for the binary search trees. There we go. Okay, sorry for my misspelling. And so I'm going to have struct node over here. We're going to have a node is pretty much just a placeholder where we keep our data. So, and this form of data can be any form, but we're just going to use integers in this case. So int data, and typically trees have a left child and a right child as well, with one node especially being the root. So that means we're going to have a node indicating for on the left side, and then node indicating on the right side as well. And then we're going to put the value of the node inside the respective data for both the left. This is how we initialize first. We'll do null pointer, then right null pointer as well. And this is how we initialize everything thus far. Don't forget your semicolons too. Now we're going to define our binary search tree class, which means we're going to have a class called bstPrinter, and the number of, and really what we're going to be doing is that we're going to have two functions really, but we're going to call them the same thing. So this is sort of like a element of recursive pattern design. So what we'll be doing is that we're going to have our public instance, and then we're going to have our private instance. This is just a way to be able to organize logic between different functions that one will be able to use to be able to call upon and be able to make one's code cleaner to write. So what we'll be doing is that we're first going to do public over here, and I just want to be sure. Also, don't forget your semicolons at the end. So that means what we'll be doing, and I'm gonna put this as private. So this public instance, what we will have is that we are going to have a function to print the tree. So this will be the actual function to print the tree, and then the private instance is going to construct the tree to print based on the height, because we're going to have different values depending on which tree as well. And this is the actual function that we're going to be calling inside of our main file over here when we build out our binary search trees. So what we're going to do is call void print tree for node root constant over here. If the root doesn't equal null pointer, we're going to return. Then int h equals height for the root, and int width is going to indicate the width of the tree at the bottom level. So we're doing it from the top all the way to the bottom, starting from the root. 1 is less than h, the height root. -1. Since we need a decrement. And the width will actually get wider as well. So, and then we're going to use a vector of strings to output the height with the respective width. So h times 2 with a string of width times 3, indicating for each space that we have respectively. And we're going to print the tree from the root, 0 most, with an output. We just need to initialize so that way we can use it later. And then this means we're going to use a for loop to be able to take in our data and then output our following. So constant auto and line output, and count line and L. There we go. Now what we will do is then go into our private instance. There we go. Let me just structure this. So this will be a function to calculate height of the tree. Int height is going to be node with respect to the root. Constant state, if the root equals null pointer, we will return 0, and then we'll also return the max height with respect to the root on the left side, and we'll do the respective height for the root on the right side. +1. There we go. And now we will create our helper function. Helper functions will be a big key theme for us throughout our binary search tree lecture series part. Pardon me, sorry. So now we'll have void print tree. This is the function that we'll call. And this means we're going to have a node, int level, int, yep, left. Let me just see if I can put this out. There we go. So that way you can see exactly what we're calling. Int left, int right, and we're going to have a vector, a string, and output for a constant state. Perfect. So notice the parameters that we have over here we also have them up here as well. Notice the relation. Now the next part we'll be doing is that we are going to initialize a null pointer. So if node is equal to null pointer, we're going to return. Then int mid is equal to the left plus the right divided by 2. And then we have to see the middle in particular. So left plus right divided by 2. I'll put the left and right side based on height and width. From the middle. There we go. So we're gonna have an output based on the respective level. Mid times 3. That is what we're calling over here. Equal 0 plus the node with the respective data. Notice the arrow pointing as well as the data that we have made initially to be able to put inside. So that's what we're doing with respect of the 10. Now we will do left. Now we're going to do right. If the node at the leftmost right here, then we are just going to make sure that we're on the leftmost side. Next mid equal the left plus mid divided by 2, and output the level plus 1 next mid times 3 plus 1 equal this branch over here that we're going to indicate. Then we're going to print the tree from the nodes left side level plus 2 left mid, and then output. Now we're going to do with the right side. So we got to do, we can literally just do the exact same thing that we did over here, except for we are going to be doing the right. So I'm just going to double check on here. If the node is directly at the right, actually just make sure that you have your, just keep things clean. Right here. I'm going to go into mid plus right. Put level, yep, plus 1 next mid times 3 minus 1. This is for the right. I'm going to print the tree node at the right level plus 2 mid right and output. There we go. Let me end if. So this is what we're going to do. This is how we're going to build out our rightmost and leftmost side for a tree. Then we print the tree. Then we initialize our height with respect. Let me just double check to make sure it's all good. Then we have our actual function that we're going to call upon to be able to print out said tree. So let me just compile, make sure it's good. All right, build succeeded. Let me just zoom out a little bit. There we go. So this is our header file for a binary search tree that we're going to be using throughout all of our lecture series. And without any further hesitation, let's head over and focus on building out our full binary search tree with our respective problems. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.